So I just wanted to briefly go over and raise a couple questions for the new paper that just came out like 2 days ago. So as you can see, this is the energy-based transformers, and I'm pretty excited about this actually because when it comes to energy-based models, there really hasn't been a whole lot of releases like over the last couple of years, and nothing that's really been getting a whole lot of attention. So like even if you just go to YouTube, for example, you just type in energy-based models, like all of the talks on it were like 4 or 5 years ago. And then like most of the videos that are even like recent about it, most of them are mainly just like AI generated, like either the Google Notebook, like the two people sitting down talking about it, or just some other like AI narrator type thing. So let's just go here. So I just wanted to bring attention to some of the comments too, because they actually do have some insights into the actual paper. So like for example, he's talking about, what is the architecture of the actual energy-based transformer? There aren't really any diagrams of it. And then Alexi's saying the autoregressive models were built on top of the Llama 2 transformer, and the bidirectional models were built on top of the diffusion transformer. So what is the difference between energy-based transformers and regular transformers architecturally? Is it just the output prediction format? So for bidirectional models, yes, the output prediction is the biggest difference. In addition to where predictions are made, the input space for autoregressive models, we do a lot of work to add a specialized implementation for parallelizing all predictions simultaneously without leaking information. So just a couple, or just like a brief and basic overview of the actual core of the model itself. And then this is just someone else bringing to attention a use case for this. Energy-based transformers could transform fintech innovation in digital hubs like the UAE. We'd love to hear your take on real-world applications. Thanks for the kind comments. I think in the short term, the biggest application will be data-bound domains, financial transaction processing, security, like around banking and accounts, things like that. So the application will be data-bound domains, as energy-based transformers are more data efficient than the standard transformer plus plus. In the long term, I'd say the application should be pretty general in anything requiring more reasoning. Data efficiency is a huge win for fintech, especially where compliance is key in the UAE's digital ecosystem. What's the biggest challenge you see for deploying them at scale? So not familiar with the UAE digital ecosystem, but I think the most challenging part of scaling will be figuring out how to get them to run faster on modern hardware as well as training stably. So yeah, I know even from like a couple years ago, that's been like one of the biggest challenges was again pretty much the way that energy-based models are trained. They're not really compatible with GPUs and how they operate. The transformer, despite the fact of it not being the best model in like really anything when it comes to like speed, efficiency, it really shines in its compatibility with GPUs and the fact that it's just so easy to train when it comes to them. So it has multiple papers up. So that it has the main paper, of course, which is the ARXIV, about 45 pages. And then they have a blog post kind of going over in further detail about the architecture. And then on top of that, they actually have a separate Hugging Face paper right here. But I think this is just kind of oh yeah, it just has the abstract for the main paper. Okay, so I can close this one out. So just before I get into the main paper, I just want to go over some basic information about the energy-based model and how they're trained and some of the challenges about that. As you can see, this was from November 2024, so a little while ago, but still most of the things in the challenges here are going to be related to the energy-based transformer. So let's close this. So energy-based models offer a compelling alternative to traditional probabilistic neural networks. They associate an energy value with data configurations where lower energy indicates better agreement with the model's learned representation. So anything within the data should have a lower amount of energy, and anything outside of the data should have a higher amount of energy assigned to it. So this framework provides advantages in flexibility, so representing complex multimodal data distributions, robustness, handling adversarial attacks and noisy data, and generative capabilities, generating new samples by finding low energy configurations. However, training EBMs effectively requires addressing challenges like vanishing gradients, mode collapse, and trivial solutions. So our approach to training in EBM involves a systematic exploration of the architecture, so reducing model capacity, batch normalization, activation function selection, regularization, and energy regularization, optimization, learning rate adjustment, and the optimizer selection. So I know Atom has been pretty popular for the past couple of years, but I do think there was actually a optimizer that did outperform Atom in a lot of different models. I forgot the name. I believe it was like Line or something along those lines, but I definitely want to go into that in another video, just like comparing the performance of these different optimizers. But yeah, I mean, again, Jan LeCun, he was one of the biggest proponents of energy-based models a couple of years ago. I know that he also had two other systems, and these are like pretty much three stacks of distinct models, right? So you have the energy-based model, you have the JEPA, so the Joint Embedding Predictive Architecture 1 and 2 was actually released very recently, so I'm going to go over that as well. And then on top of that, he also had another separate system, the large concept model, where basically the model does not operate on a token level. It doesn't predict the next token. Instead, it operates on a sentence level, where essentially it has the ability to more intuitively understand abstract concepts. Now there is, a benefit and a downside to that. So when you're taking out tokenization from, a model like the large concept model, you lose the ability to have fine-grained control over the exact level of understanding that the model has when it comes to these concepts. So when you're working in, let's say for example, you just want to have the large concept model be used as like a chatbot or something like that, it's really not going to be a big deal because you don't really need to have extreme precision when it comes to just somebody like messing around, like, just trying to, play around with it like as a demo or anything. But when you're, talking about like a scientific deployment, anything for like research, obviously you're going to need a model that has the absolute highest amount of control over the conceptual level of understanding, because even if like a value is slightly off or it's misinterpreted, like let's say you have a formula, for example, it's like 15 to 20 different symbols. If even one of those symbols has been misinterpreted or left out or whatever the case may be, then pretty much the whole equation is wrong, and it pretty much throws off the entire experiment, and the results of that experiment can pretty much be worthless. So I do like this aspect where it goes over the hierarchical representation. So where basically energy-based models excel at tasks which require a higher level of understanding and like a multi-step and multi-function level of understanding. So let's say, for example, you're trying to learn how do transformers work, right? So you have all of these different aspects of it, right? You have at the highest level, which is like the highest level of abstraction, um, on top of the attention mechanism, on top of the tokenizer, the optimizer, like all of these different moving parts that kind of make the large language model sort of work. And of course, there's a big difference between a multimodal LLM where they have the ability to generate images, they can connect to the internet, they can do all these other type of features, versus just a bare bones transformer which doesn't have any of that. They don't have the ability to break down like a video or like open a PDF or whatever the case may be. So there's like a broad range of capabilities when it comes to like language models and how they're actually being built and designed.